For the introduction. It's my great pleasure to be here, and I have some last moment change of the title because I think that's something more interesting for me to talk about, which is really our more recent result on the study on the energy efficiency of larger scale optical neural networks. And it is really great for me to give this talk after Ryan's talk because the topic is really match well together. So one of the important questions in the field of optical neural network people are caring about is, can we use, optical neural networks are analog computers. Can we use analog computers to perform state-of-the-art machine learning models like the ChatGPT you just have seen? And in this talk, I will tell you most likely yes. And the second question is really just you have seen a tremendous effort in scaling up optical neural network hardwares, from Ryan's talk. And now, even though we are still a little bit distance away from there, but assume if we can scale to 1,000 by 1,000 image size, right? Can we really use them to achieve much better efficiency and run the best language models there? And this talk, I'm also going to tell you most likely yes. So the talk is going to be more like a tutorial. So I will start from basics and the backgrounds, and I will only go into the more recent results towards the end. And I also try to make it more accessible to the imaging community because I just realized a lot of people have an imaging background. So before I dive into the topics, I first would like to acknowledge everyone who contributed to the work, and you will see students' name flashing up here and there during the talk. So as we all know, like artificial intelligence is going to change our life. They are everywhere in the software, running on the computer, and on the internet. They are running hardware like self-driving cars and industrial robots. So as this model is getting like more and more sophisticated, they create a problem, which is the amount of computation they need far exceeds the capacity of hardwares. And for most of the machine learning models, we are trying to do essentially the same task as this one, which is to find a function that can, when it's given a dog picture, it generates a label dog, and when it's just given a cat picture, it generates a label cat. So it turns out that it's really hard to handcraft this kind of functions, and therefore, so far people realize neural network is the best solution to this kind of problems. And the so-called neural networks are just the layers of simple linear and nonlinear operations laid out in the interleaved way. And in this way, there were so many parameters in these models, and all we need to do is to fit for these parameters to approximate these functions. And in order to figure out these parameters, we need to use a lot of training data sets, which are essentially pairs of images and labels. And as neural networks get more and more powerful, they're getting deeper and deeper. Therefore, people call them deep neural networks. And it turns out that this kind of method not only works very well for classifying dog and cat pictures, it goes far beyond this. For example, they are the best algorithms for computer visions. They are best algorithms for natural language processing. They are the best algorithms for playing games. And they can simulate the physical systems like protein folding that was once thought to be impossible to solve with starting from the first principles. And more recently, they are starting to generate the contents, like they can generate the image based on text prompts of things that had never existed in the world before. And the key to the success of these tasks is to make a bigger neural network, which means it's deeper, wider, more parameters, more computation, and needs a lot more training data. And therefore, the state-of-art machine learning models are growing at a speed that is about 750 times of computer demand for every 2 years. And in comparison, like for digital electronics, whether you agree Moore's law still holds or not, it's like double every 2 years. And people have been putting a lot of efforts into developing so-called application-specific hardware, which is processes are optimized for machine learning algorithms. But you see that here it only generates an offset on the log scale, and it does not really fundamentally change the scaling law. And therefore, in order to have sustainable machine learning applications, we really needed to seek some fundamentally different hardware platforms. And this computational gap really motivated us to explore alternative hardware platforms, and that's why we are considering optics here. So why optics? So here I just wanted to give us the simplest example to make you understand that optics has a different scaling law than as from electronics, and they are really good at a large-scale efficient linear transforms. And this example is just basically using a lens to do a Fourier transform, which is very familiar example to everyone doing imaging. So a lens basically can perform a Fourier transform of the optical field in one of its focal plane to the other. And if you look at this computation carefully, you see that the number of the amount of power you need to operate this computation is basically determined by the number of emitters and the receivers that scales with n. But the amount of computation you have done, which is a discrete Fourier transform, that has a matrix size of n times n, which is n squared. And therefore, the energy consumption for each multiplication in this discrete Fourier transform actually scales inversely with n. That means if you have a larger n, you actually have energy amortization and you spend less energy on each multiplication. And some of you say, wait a moment, if you increase the n, don't you spend more optical powers as well, right? And that optical power energy actually scales with n squared. And in this talk, basically, I'm trying to tell you that n squared optical energy is negligible, and therefore the majority of energy is determined by this emitter and the receiver energy that is related to electronic overheads, and therefore this inverse scaling law of optical computing works, and that's the advantage of optical computing. Here, I just want to show you that why this kind of optical processes are really efficient for implementing neural networks. Here is a typical neural network. It's a fully connected multi-layer perceptron, and you take an image as input, and for image, it's 2D, but you can flatten it into 1D vector, and then this serves as your first layer of activation, and based on this, you calculate the next layer of activation, and you do this layer by layer. And a lot of times it involves very dense connections from the previous layer to the next layer. And this is very similar to what you have just seen in the Fourier transform with a lens, which is essentially it involves very dense connections. And therefore, the goal of all sorts of optical neural net hardware is really to implement the matrix vector multiplication part of the neural networks, which accounts for the majority of computation in deep neural networks. And by efficient implementation of this process, we can achieve better overall energy efficiency. And that's the motivation of the whole field. Here's Wright's work again. So basically, theoretical prediction has already shown that as you go to larger and larger n, which is the width of a neural network, your neural network is more and more efficient. And at some point, it's the amount of optical energy is even smaller than so-called Landau limit, which is the fundamental energy limit of irreversible electronic computation dictated by thermodynamics. And this is at the level of several attojoule or 10 to the minus 18 joules, which is extremely small amount of energy. And when we first saw this, we thought that it was too good to be true, and therefore we really wanted to do experiment to test how viable this regime is. And this is exactly the regime we are interested in, which is quite a large and at least a couple of hundred in terms of matrix size. And in this region, it was predicted that we can optical neural network could achieve a really high efficiency. And the way we did that in the lab was kind of straightforward. This is the very straightforward but scalable way to experimentally implement optical vector dot products. So for the first vector, we just wrap it as a 2D array, and for the weight vector, we also wrap it in the same shape. And for the input vector, we just encode each element as the intensity, and for the second vector, we encode each element as the transparency of a spatial light modulator, and then we align them pixel by pixel. And then after this spatial light modulation, what we get is essentially an element-wise product between the two vectors. And then simply we just use a lens to focus all the light onto one single detector, and that performs the summation. And then we get the result of vector-vector dot product. This is a very small scale, but it's used 2D, therefore you can make a very big vector. So there, just give you a sense, like here, these are our experimental data, like we can put the whole images, and you see here's element-wise products, and here's what the setup look like in the lab. It's irrelevant, it's just a setup used to really test the property of optical computing, and the result can be generalized to a lot of different setups as well, like architectures as well. And in this experiment, in order to really study large models, which you will later see to be important, the setup can compute vector dot product size with a vector size up to about 0.5 million, and that really enables us to study very state-of-the-art models. But for the first experiment, we did a very simple thing. It's the hand-rated digit classification again. So we made a multi-layer perceptrons here, and then we used our optical dot product to perform all the matrix vector multiplications involved in this model. And then I also need to mention that for the bias term and the nonlinear activation functions, we use a digital computer to perform, but they scale with the n, but the matrix vector multiplication scales with n squared. Therefore, majority computation is still in optical domain, and the digital one is kind of inevitable in all architecture, but they don't account for the majority of energy. So. And then we, from using this model, we wanted to really see when we keep decreasing the amount of optical energy, what would happen, right? So what prevents us from infinitely decreasing the optical energy? So here's the concept of shot noise. For those of you not familiar with already, so here's a noisy image of noisy photo, and when you zoom into a part of the photo, what you see is like the pixels are quantized, so they're either black or white. And if you look at the histogram, it's either 0 or 1. There's no like continuous gray values in between them. And it turns out that they conform to a Poisson distribution, which generally applies to all sorts, most of the kind of light, except for the exotic quantum light. And for Poisson distribution, its signal-to-noise ratio is proportional to the square root of its mean. And therefore, when you have a low mean number of photons, you have a very low signal-to-noise ratio, and it makes it really hard to see the information in your image. And for most of you having done imaging, this is a very familiar thing. And for the same image, when you increase the amount of light exposure, it becomes more gradual and grayscale. And if you look at the same area, it looks you can tell more details there. And it turns out that the only difference is that you have much higher average photon numbers for the Poisson distribution, and therefore you have much higher signal-to-noise ratio, and that gives you more information in the image. And this does not just apply to photography or imaging. This phenomena applies to any kind of photometry, including optical neural networks. And this is the phenomena that prevents us from going to really, really low optical energy. And here is the consequence. So here we are showing the accuracy of the neural network I just talked about as a function of optical energy put into the system. And here I first show you is a simulation which is essentially running the neural network on the computer, but with a simulated shot noise. And at high optical energy, as you see, it achieves very high accuracy at 99%, which is essentially the same as a digital computer. But as we decrease the optical energy, the accuracy, of course, starts to drop because of it suffers from a low signal-to-noise ratio, and then eventually it becomes 10%. It's a random guess level because there's only 10 digits, and a random guess would give you 10% accuracy. And then here we show the experimental data. They agree reasonably well with the simulation. And one interesting thing we finally saw was that at even less than 1 photon per scalar multiplication, we could still achieve 90% accuracy, which is quite surprisingly high. And at this level, if you look at the total amount of optical energy in that neural network, the entire neural network to classify the image, it was about 100 femtojoule optical energy. And there were altogether 90,000 multiplications in that neural network. And just give you a reference, like multiplying two 8-bit integers with 7 nanometer node, like electronics, takes about 70 femtojoule. So this is like really tens of thousands more efficient than digital electronic computation. Okay. But you may say, wait a moment, you are only counting the optical energy here, right? And there should be electronic overhead. There's like digital to analog conversion. There should be optical to electronic conversions. So the actual whole system energy would be much lower. That is correct. But later I will see with a scaling law, this will enable us to do to even achieve a whole system energy advantage. So first, like there were multiple layers of significance with this result, but first we need to interpret the result correctly. So what does it mean by less than 1 photon per multiplication? So here I just give you a picture, like say, assume you measure the photons in a single beam, you can only get an integer number of photons, like 0 photon, 1 photon, 2 photon. It's not possible for you to get a 0.5 photon. But when you have many beams focused together onto the detector, like you can get a large number of photons, and then but you divide the number of beams, the beams here, you can get a fraction of photon numbers, and that essentially means. And this fraction photon number can be less than 1. And this essentially means that some of these beams are not really contributing to the computation. However, nevertheless, the neural network still works, which is the surprising part. So here we just get a closer look. So normally traditionally people think optical neural networks as analog computers, which means the vectors are continuous value variables, and then the result is also continuous value variables. But as you see, as we decrease the amount of optical intensity, the sharp noise becomes obvious, and we need to replace this continuous variable with random variable conforming to Poisson distribution. And therefore, we start to have a sort of a stochastic optical neural network where the input are stochastic variables. The output, in principle, is also a stochastic variable, but because there are so many terms added up, so it has a very high SNR. So you can think of it as quasi-deterministic or continuous variable. For example, like in our experiment, we typically have at least a 4-bit equivalent resolution, and it's up to 9-bit equivalent precision at the output. And in this region, we have just shown that the optical neural net would perfectly work fine, at least for simple task of image classification. And actually, we can go even one step further. If you think about this stochastic neural network, it's basically you are measuring the number of photon arrival events within a time window. And if you keep reducing the time window to extremely short, then we are in a regime that we are just getting either 0 or 1 photon, not more than 1. And in this case, the distribution becomes a binary distribution. It's either 0 or 1. You don't get any more. And but the input is so low so that the output becomes stochastic as well. It also becomes binarized. So now both input and output can be stochastic. And there were some technicalities here, say how we conduct experiment with photon number solving cameras and how this single photon detector causes some nonlinearities. I'm going to skip on this, but the result is really that this kind of neural network still works, and then we show that it can further reduce the amount of optical energy by 10 times compared to before. So before I show you for classify each image, it took 100 femtojoule. Now it's like on the order of 10 femtojoule. And you may say, wait a moment, your output is stochastic. How can you do a deterministic task like image classification? Can't you get it right all the time? You're right. And what we did was we only allowed this binary stochastic variable in the hidden layers. And in the last layer, we still have a higher signal to noise ratio so that the output is deterministic. But since the last layer is small, so it does not account for the majority of energy. And this, we're really showing that optical neural network can work in a very exotic regime that based on the stochasticity of a single photons in this experiment. So here, I'm pushing to the order limited to the optical energy. We see that optical energy actually accounts for nothing in optical neural networks, and that's the basis of the scaling law. As we said again, so the overall energy actually mostly scales with the input and output n, but not the total number of operations. And therefore, in optical neural networks, it scales with the analog digital conversion and the electro-optical conversion. But instead, in the digital computers, when you increase the n, the amount of analog logic units, arithmetic logic units, and the memory increase is not negligible, and therefore the energy goes up more steeply with n, roughly with n squared. And therefore, this is the scaling of optical neural network, even though it has a high overhead for small n because of all the light and electronics conversion, but it decreases more slowly with n, and eventually there's a crossover point with the electronic hardwares. And the key is really where the crossover point is, and do they have unrealistic neural network models? And for this, to study this question, we think it's ideal to study large language models, which are transformers. Basically, they are the same architecture underlying ChatGPT. And for these models, they are typically very large, and they involve dot products that's larger than 1,000 in dimension. Here, I give you a glimpse of it. This is just one head of it. There are so many layers, and this, like the whole model is 20 times larger than this. And here there's a lot of like 1,000 dimension kind of multiplications. Remember we had our setup that can handle this kind of multiplication. Therefore, we picked out some important layers here because at this moment we still cannot run the whole model on the setup. It took too long, like weeks. So we pick out the important layers, run our setup, and then we summarize their noise characteristics, and we concluded that these transformer models can actually run with about the 4 to 5 bit precision. And here is really basically a 2D landscape, a contour map showing that like how performance depends on the precision of different parts of a neural network. Okay. So without further delay, based on these noise characteristics, and we conduct a simulation on even larger models. And here we really show is that for say for GPT-3, which is a state-of-the-art neural net model with this conservative estimation, optical neural network can achieve about 70 times the overall system energy advantage over the state-of-the-art digital electronics. And state-of-the-art electronics is about 100 femtojoule per Mach, and 10 femtojoule per Mach is a very futuristic kind of a GPU. And optics here has a much flatter slope as we get into larger model size. And therefore, for larger models, optics has more advantage in these gigantic language models. And therefore, as a summary, we show that the optical neural network can consume an extremely low amount of optical energy, and they can conduct computing in a stochastic regime, even with single photons. And it applies for language models and image processing, and this serves as the foundation for a very favorable energy scaling for large, extremely large models. Yeah, thank you for your attention. That's the end of my talk.